Hello, welcome to another module in this massive open online course. So, we are looking at example problems in the Fourier analysis of discrete time signals. In particular, we are looking at the discrete Fourier transform, alright. So, let us continue our discussion. So, we are looking at example problems in DFT, okay. And well, let us continue our discussion of the previous problem. So, we have the signal xn equals sine pi by 2 n 0 less than equal to n less than or equal to 3, which basically turns out to be the sequence 0, n equals 0, this is 0, 1, 0, minus 1, all right. And further the sequence Hn, or you can consider the impulse response of the system Hn to be 1, 2, 4, 8, and Yn equals xn circularly convolved with Hn. So, this is xn circularly convolved with Hn, correct. This is your circular convolution. Hn circularly convolved with Hn. We have implemented this in the time domain, correct, the circular convolution between these two signals in the time domain. Now, we want to implement it using the, or now we want to evaluate it using the DFT, okay. So, evaluate the circular convolution using the properties of DFT. And what we have is, now the DFT can be evaluated as follows. Now, if you want to use the DFT, realize that we need this factor Wn, which is in fact W4, which is e raised to minus j 2 pi divided by n, which is e raised to minus j 2 pi divided by 4, which is e raised to minus j pi by 2, which is equal to minus j, okay. So, Wn is minus j, okay. So, this quantity Wn, which we use in the evaluation of the DFT, is minus k. Now, therefore, our quantity x k, the kth DFT coefficient, can be written as summation n equals 0 to n minus 1, that is 3, 4 minus 1 is 3. So, n minus 1 xn Wn to the power n, Wn raised to the power kn, I am sorry, Wn raised to the power kn. So, this will be n equal to 0. So, x of 0 is 0. So, this will be x of 0 into Wn raised to the power of 0, that is 1, plus x of 1 Wn raised to the power of n, or sorry, Wn raised to the power of k, plus x of 2 Wn raised to the power of 2k, plus x of 3 Wn raised to the power of 3k, all right. This is the expression for the. Now, out of this, observe that x of 1, observe that x of 0 is 0, x of 2 is also equal to 0. So, these two terms are 0, and what remains therefore is the term corresponding to x of 1, which is basically 1 raised into w n raised to the power k plus x of 3, that is minus 1 into w n raised to 3 k. So, the kth DFT coefficient of the signal sin pi by 2 n is w n raised to k minus w n raised to 3 k, where w n, recall, is minus j for this case. Okay, all right. And similarly now y of k equals summation n equals 0 to n minus 1, that is I am sorry, this is h of k, this is h of k is h of n w n raised to the k n, which is h of 0 is 1 plus h of 1 is 2 w n raised to the power k plus 4 w n raised to the power 2 k plus 8 w n raised to the 8 w n raised to the I am sorry, w n raised to the 3 k. This is the expression for your h of k. Okay. And now observe that the DFT of the output is the multiplication of the DFT coefficients of the input. So, y of k, that is you will have y of k, because you have a circular convolution in the DFT domain, it becomes multiplication, that becomes x of k into h of k, which is basically w n k minus w n 3 k and its product with 1 plus 2 w n k plus 4 w n 2 k plus 8 w n 3 k, and we will multiply this, realizing the property, using the property that w n, here w n is w 4. So, w n to the power of 4 k is in this case e raised to j 2 pi by 4 to the power 4 k, which is equal to e raised to j 2 pi k, which is 1. So, w n raised to the, so in general w n raised to the power of n k equals 1. Okay. In this case n is equal to 4. So, n is equal to 4 in this example. So, n is equal to 4 in this particular example. So, w n raised to the power of 4 k is unity 1. We will use this property in the simplification. Okay. So, we have y k, you have y k equals w n k minus w n 3 k into 1 plus 2 w n k plus 4 w n 2 k plus 8 w n 3 k. This is equal to, now you can simplify this as w n k into 1 minus w n 3 k plus 2 w n k into w n k, that is w n 2 k minus 2 w n 3 k into w n k, that is w n 4 k, which is 1. So, this is simply minus 2 plus 4 w n 3 k minus 4 w n 3 k into w n 2 k, that is w n 5 k, but w n 4 k is 1. So, this will simply be w n k plus 8 into Wn3, 8 Wn3k into Wnk is Wn4k, which is 1. So, this is simply a plus 8 minus 8 Wn3k into Wn3k is Wn6k, which is Wn4k into Wn2k. So, this is simply Wn2k. So, this is equal to, now if you look at this, you have 8 minus 2 is 6. 6. Now, collect the coefficients of W and K, that is 1 minus 4 minus 3 W and K. Now, collect the coefficients of W and 2K, that is plus 2 W and 2K, minus 8 W and 2K, that is minus 6 W and 2K, and W and 3K. Now, you have minus, you have 4 W and 3K minus W and 3K. So, 3 W and 3K, and if you compare this with the DFT, that is I0 plus Y1 Wn K, if you do a term by term comparison, Y2 Wn 2K, you can see y0 equals 6, y1 equals minus 3, y2 equals minus 6, and y3 equals 3. So, what? So, by doing a term by term comparison of the DFT, you can deduce the coefficients of the DFT of y, that is the coefficients yk, all right, by looking at the coefficients of the expression, okay, and therefore, what you have is y0 equals 6, y1 equals minus 3, y2 equals minus 6, and y3 equals and remember, this is identical to our what we have derived from the time domain evaluation. So, we have evaluated this using the DFT, also evaluated the circular convolution in the time domain, and of course, both of them yield the same answer, and that is basically, this serves as a check. So, each serves as a check on the other, okay, all right. So, let us proceed to the next problem. This was, I believe, if I remember correctly, this was the 18th, problem. So, let us proceed to the next example, that is example 19. Example number 19, what we want to do is we want to find the DFT of e power j naught e raised to j omega naught n 0 less than equal to n less than equal to n minus 1, okay, and under the condition omega naught is not equal to 2 pi k over n. In this case, xk equals summation n equal to 0 to n minus 1 xn wn kn, which is equal to, well, this is equal to summation n equal to 0 to n minus 1 e raised to j omega naught n wn kn, which is equal to, this is a finite summation. So, this is summation n equal to 0 to n minus 1 e raised to j omega naught into wn k raised to the power n, okay, which is equal to, in this case, well, this is 1 minus e raised to j omega naught n wn k n over 1 minus e raised to j omega naught wn raised to k. which you can now simplify this as, well, this is 1 minus e raised to j omega naught n e raised to minus j w n k n is again 1, or you can just simply write it as e raised to minus j 2 pi k over, just write this, although this is 1, one can just write this as e raised to minus j 2 pi k over n raised to the power of n e raised to minus j omega naught e raised to minus j 2 pi over n, or e raised to minus j 2 pi k over n, which is equal to, this will be, if you can check this, this will be 1 minus e raised to minus j omega naught minus 2 pi k over n raised to the power n, 1 minus over 1 minus e raised to minus j omega naught minus 2 pi k over n, which is equal to, simplify this, e raised to j omega naught minus 2 pi k over n into n by 2 e raised to j omega naught minus 2 pi k over n into half, this multiplied by e raised to minus j omega naught minus 2 pi k over n into n by 2 minus e raised to j minus e raised to j omega naught minus 2 pi k over n into n by 2 divided by e raised to minus j omega naught minus 2 pi k over n into half minus e raised to minus j omega naught minus 2 pi k over n into half, and this, if you simplify this, what you will obtain is e raised to minus, or e raised to j, in fact e raised to j omega naught minus 2 pi k over n into n minus 1 by 2 into sine omega naught minus 2 pi k over n into n by 2 divided by sine omega naught minus 2 pi k over n into half. So, this is the expression for your DFT coefficient, that is x of k. This is the expression for the kth DFT coefficient, that is e raised to j omega naught minus 2 pi k over n into n minus 1 over 2 times sine omega naught minus 2 pi k over n times n by 2 divided by sine omega naught minus 2 pi k over n into half. All right. So, this is the expression for the kth DFT coefficient of the given signal. All right. Now let us do another interesting problem, which is to express the DFT as a linear transform. Okay, so what we want to do is we want to express this DFT as a linear transform, or DFT in the form of a matrix, and this is, if I am not mistaken, this is problem number 20. So, the DFT can be expressed, or DFT, and in fact DFT So, the DFT and IDFT can basically be expressed in a matrix form, all right. So, what we will do is, because we have done a couple of examples, let us stop this here and we will look at this fundamental aspect in the next module. Thank you very much.